Welcome back to the Copernicus Land Monitoring Service. This is Submodule H, finally addressing the Copernicus Global components, services and products, dealing and addressing with agricultural applications specifically. So, first of all, the global component services are operational services which provide long-term and reliable global products and services in a near real-time fashion and from a consistent archive of biophysical parameters on the land surface. They address features on a medium to low resolution based on the respective Earth observation sensors, and they provide data in a fully validated and quality controlled fashion. They allow for doing a wide range of applications starting from water management, land cover and use changes, forestry applications, desertification measures and combating, biodiversity applications, natural resources management and monitoring, and most and foremost, agriculture and food security applications. They provide direct support for the policies of the European Union, for commitments under international treaties and conventions, and they provide also key contribution to the Global Geo Initiative under various further sub-initiatives. Copernicus and the global products are a public good. They are available under free and open access. And one should add that the global component as part of the Copernicus Land Service has a long heritage which goes back even to 2008 through several research and development initiatives and activities resulting in its initial operations, which started in 2013, which meanwhile have moved into its second phase since this year, 2016. The global land component consists of four basic subcomponents. First, the continuous daily monitoring of land surface. Second, the in situ collection of ground truth. Third, an ad hoc monitoring of specific hotspots at very high resolution over protected areas. And fourth, the generation of application-ready data from Sentinel-2. The global land component provides also long-term and reliable provision of products and services for downstream applications, so that's further value adding. And it delivers fully validated and quality controlled products and services to support and consolidate to various international policies and commitments that both the EU and member states have to follow. The operations component is an operational service providing free and open access. It supports a wide range of applications, as I mentioned, water management, desertification, and so on. Well, if we look to the next slide, basically there's a lot of users making use of these various kinds of products. There's a global user community, but also national and local user communities. Global communities basically comprise users in, meanwhile, more than 60 countries. They comprise the European Commission through various institutions, for example, the JRC and the Mars unit. The users comprise also international organizations like the United Nations and its food and agriculture organizations or the World Food Programme. And furthermore, the global component services contribute also to developing and capacity building. For example, under the GMS for Africa programs and various other related activities together with the African Union, as well as these services are used locally by national governments and institutions, by private companies, by civil society and NGOs, and also by a wide and growing research community. Basically, these global land services are a key European infrastructure, and the majority of users, that is more than 50%, are basically European. The portfolio of global land products is rather large. It's structured along three main aspects related to vegetation, energy, and water fluxes on the Earth's surface. There's a lot of parameters being operationally monitored in near real time. That means 10 daily or even more frequent time steps. They provide consistent time series, which allow to monitor anomalies in the time series and also trends, which can also allow to give prognosis for forecasting of the development of certain of these parameters. They're typically monitored at low to medium spatial resolution, meaning 1 kilometer, 300 meter down to 100 meter. So there's a lot of efforts ongoing to increase or to really improve the spatial resolution also in that respect. I won't go through all the parameters, just to mention a few. In terms of vegetation, there's vegetation indices like leaf area index or normalized different vegetation index, or there's also other indices like fraction of vegetation cover, fraction of absorbed photosynthetically active radiation, and so on. What you see in blue here, greenness evolution index, phenology metrics, and so on, that represent plans for further evolvement of these parameters in the future. So the target time frame is 2019, when it's expected that the variables that are available under the global component will more than double. And this affects both the vegetation-related parameters, but also, and even more, the energy-related parameters. So there will be further parameters on radiation fluxes, fires, and so on, also evapotranspiration. And if we look at the water fluxes, the impact will be even bigger. There will be further parameters added, like on coastal erosion, lake surface reflectance, lake turbidity, and so on. And there will be a new component added on the cryosphere comprising the Earth's ice and snow-covered areas. So there will be features on snow water extent and snow water equivalent, which are planned to be monitored also operationally. Plus, there's of course also components on in situ monitoring, hotspot monitoring, and also Sentinel-2 applications. This all, has to be said, is still tentative and is intended to be implemented by 2019. The global land component is working to include also the Sentinels 1, 2, and 3. Some examples would be the use of Sentinel-1 for soil water index, or Sentinel-2 for land cover, also 100-meter resolution, Sentinel-3 for many vegetation products or for lake surface temperature. And there's further applications like hotspot monitoring. There have been contracts placed earlier this year. And basically all this is in a startup phase, and there's further applications coming on top, like Sentinel-2 pre-processing, which will be issued soon and is expected to start in 2017. So this is a whole bunch of activities and components and services that are implemented on the global land component. In terms of agriculture, which is the main topic of this talk, there are several parameters which have a main impact or which have a main meaning and meaningfulness to the agricultural services and applications. Just to mention a few, it's the LAI, FRPAR, and F-cover. It's burned areas, which obviously have an impact on vegetation area and healthiness. There's the dry matter productivity, soil water indices, and also other upcoming or in planning indices like greenness evolution, phenology, evapotranspiration, and so on. All these indices are or will be processed for time series starting as early as the late 90s, depending on the availability of satellite observations. So you see there's satellites with resolutions starting from 100 meter to 300, 1 kilometer, and so on. And you see also that there's not only the coarse resolution satellites, but there's also the Sentinels, meanwhile added to that list, and they're intended to be also operationally used for that global land product processing. The global land service has various components that are overarching, cross-cutting to all these services that are provided as a service to users, like there's a website and a mailing system which allows the users to discover and to inform themselves. There's map and time series viewing capabilities, and I'll show some examples in the next slides, which allow to really discover the products as they are made available on the websites and portals. There's product distribution mechanisms which allow the users to access the products via the web or via other means. There is mechanisms and methods to do analysis with the data, like tutorials, webinars, software integrations, and so on, that can be used. And on top, there's also help desks which can help the users to answer their questions. So one example of information sharing, this is a short screenshot of the Global Land website. The address of the portal is given at the upper left, so here you can access all the data, and the portal gives additional information in terms of short abstract and a description also of the services and the products on top of the viewing and downloading capabilities. There's the viewing services. So this is one example of a map viewer. This is, in this case, the NDVI, the Normalized Difference Vegetation Index from June 2016 in Africa. And in terms of the display, one can say that the greener the color, the higher the NDVI, and the opposite, yellowish and reddish tones, are low NDVI, thus a low or non-existent vegetation cover. This is another example of the LAI, the Leaf Area Index from September 2016 over Europe and Northern Africa, which is also a measure of the vegetation density. Green areas again represent dense green vegetation. So all this can be accessed online via the portal. Then there's mechanisms for product ordering and download. So you have these systems where you can discover, select, and make your choices of the data. There is systems for email notification when a certain order has been processed and is ready. There is subscription services which would allow you to access upcoming products in the future. And there's various kinds of customization possibilities like spatial windows, file formats, projections, and so on. So one further possibility of doing a time series analysis is the time series viewer, which can be applied to basically different kinds of administrative units. In this case, Austria has been selected, and this tool allows to do a temporal profiling of certain variables. In this case, I think it's been the LAI having been selected, and you see that you can display the temporal development of certain of these biogeophysical parameters over time. You can select the time frame, you can select the area, which allows you to do temporal comparisons between such profiles over time. You can compare from one year to the other. You can assess whether one year is a specifically early year and the development is starting early, or whether you're late in the season or whatsoever. So that really gives you tools to quantitatively make statements on the development of vegetation and agricultural areas, for example. That can be done for any area in the European Union or also otherwise. There's one further important application of the Global Land Monitoring Service, which is the European Agricultural Monitoring, which is undertaken by the Commission's JRC Mars unit. There's regular bulletins published from the official crop monitoring and yield forecasting system. These bulletins are provided on a monthly basis and provide yield forecasts for up to 10 crops. So you see one example here on the right side. And these forecasts do use, on the one hand, Earth observation data, meteorological weather data, also crop development models and statistical tools, which are combined in a synergistic manner to come to statistical statements and forecasts of how the crop or the different crops will develop over time in given regions. Several member states have adopted that system of forecasts. For example, Belgium has adopted this, and also some neighboring countries like in North Africa and Ukraine. The advantage is that the same infrastructure can be used by all these countries to analyze the climate change impacts, estimate biomass development, and so on. It allows to do trend analysis, regressions, scenarios, and so on. So on top, there's a range of indicators having been developed and are being derived operationally on top of that by the Mars unit, being based on several agricultural and meteorological input data sets. Like, for example, as you can see here on the map of Europe, in France and in Eastern Europe, there have been conditions that have retarded the development of maize. And basically the grain filling conditions in these Eastern European countries and in France were such that the maize grains just grow smaller and delayed in time. Well, basically the map of the photosynthetically active radiation accumulated over time from August to September 2016 confirms that hot and dry conditions hamper the grain filling of summer crops, both in Romania and Bulgaria and in France. So another example for yield forecasts has been conducted in Northern Africa in this case, based on assessment of NDVI and FAPAR, rainfall, soil water and whatsoever, in especially a water-limited context. And this can be also used to early detect severe conditions which will have impact on the later yield amounts of crops, which will have impacts on the local population and food security situation. Well, there's also global early warning systems being applied based on Earth observation data, like on a global scale, anomaly hotspots are detected in terms of agricultural production. This is a semi-automated warning classification system which can provide timely information both to the European Commission's Directorate General on Development Cooperation and also other stakeholders in the crop monitoring and food security domain. And in terms of further use of these bulletins and these forecasts and yield forecasts, there's also national examples of integrating these systems in their national reporting. For example, of Belgium, these forecasts are regularly being picked up by the media. It's being based on weather conditions from observations on a national level. It provides crop status information at different points in time. Well, for example, the start of the season, the harvest times, but also the detection of anomalies, like on the global scale, by comparing the actual situation in a given year with long-term statistics. And there's of course also specialized institutions doing field observations and comparing the modeled results with the in situ measurements to ensure that there's not a discrepancy, but that the model is really calibrated to the real on-the-ground situation. So these yield predictions do address, for example, winter wheat, barley, maize, potatoes, sugar beets, and other kinds of agricultural crops. And as I said, based on several kinds of Earth observation, weather, and other local observation data and models. Here's one example of an agrometeorological bulletin for Belgium. This shows an analysis for agricultural areas in 2015 based on the fraction of absorbed photosynthetically active radiation. And what you see here is different curves of crop development in terms of absorption of radiation. So you see different classes of crops. The bluish one and the yellowish one are above or at the average of the long-term development, how it should be. So basically these are good curves. And there's a red curve which goes below the long-term annual average, which can be considered a suboptimal development. Fortunately, if you look at the spatially distributed map, the red areas are in the absolute minority and most areas are developing quite fine. Another example from Belgium, this has been an event in 2011 where we had a drought event in spring season. There have been significant losses in biomass production for winter wheat, especially in the period April to June 2011. And here you can see clearly the influence of the soil. On the left side, you see the development of certain crops in an area where there's a loamy, fertile, heavy soil, which is typically wet and can hold the water quite well. So there's relatively little impact in these areas, but on other areas, which are marked in red here, which are close to the coast, which have sandy soils, which cannot hold the water very well, the impact is rather dramatic. So this is basically what one would also expect, but can be monitored by these tools in a spatially explicit manner. A further application is on the global net primary productivity modeling. The net primary productivity is associated with a carbon assimilation rate of vegetation, in this case specifically of agricultural crops. And it's a parameter that represents a key uncertainty in global discussions in the CO2 debate. So when it comes to greenhouse gas and modeling of the impact of climate change. This is one of the parameters that is not really absolutely under control, and that is very controversially discussed. So there is a statistical model having a global coverage, but also allowing a regional focus which addresses exactly that parameter. Of course, there's publications related to that, and it's been presented in various occasions. Here you see an example of the net primary productivity for Europe in 2014. Well, this all is on the global component, but now with the Copernicus Sentinel satellites being available and coming into play, there is further evolutions ongoing. Especially on the global component, there's a development towards the European land service components in terms of resolution, in terms of product portfolio, especially in terms of agricultural applications. There is a high potential for crop monitoring due to the high revisit time and the unprecedented capacities, especially of the Sentinel-1 and Sentinel-2 sensors. And it could be that this development leads to a basically crop mapping, crop monitoring service at a higher spatial resolution for Europe, and also in synergy with probably the Common Agricultural Policy land parcel identification systems. There's also applications, especially of Sentinel-1 data, for operational soil moisture monitoring. Various indices can be derived from that: soil water indices, SAR-based soil water index, surface soil moisture of the upper soil layer, probably up to 5 centimeters depth, and so on. One example of such product having been derived is the Alpine countries, specifically Austria and southern Germany here, where the surface soil moisture has been derived from Sentinel-1 in September 2015. So also an interesting and relevant application. There are pilot applications, as I mentioned, for Copernicus Land in terms of agricultural services. There have been pilot projects ongoing, both in Europe and worldwide. Target parameters and products would be seasonal crop maps, crop-specific biophysical parameters, or farming practices monitoring. And these products and services are under evaluation for potential further use in the future as land service components for agriculture. In terms of the further evolution of these services, there's already a roadmap and a schedule existing how these services will evolve towards higher spatial resolution and towards more near real-time production until 2019. So there's a lot of ideas what will improve further there. So the future is secured. Finally, I'd like to thank a lot of contributors who have made material, data and information available for this module on the global agricultural applications. Thanks a lot for the contributions. Thanks a lot for your attendance, and thanks and goodbye.